This is a heat shield that I designed and built. It can withstand temperatures upward of 3,000 degrees Fahrenheit. Today we're going to talk about what it's made out of and the purpose of heat shields. So phenolic heat shields have been around for a while now. NASA uses them, SpaceX uses them. I decided to go for a safer option. Just based on the nasty chemicals that are involved, like the resins, the curing process, it's just not something worth hurting my lungs over. Phenolic resin is a thermoset plastic that is made by curing phenol and formaldehyde together. It's strong, it chars instead of melting, and it's been used on everything from the Mercury capsules to modern Falcon rockets. But here's the thing. Making it at home or in a small lab, not great. The vapors are toxic, it's hard to control curing, and it generates a lot of heat and pressure, which you don't want unless you have serious lab infrastructure. So instead of trying to copy that, I decided to go with a different option. A Starlite-based material that was surrounded by mystery, and it always kind of fascinated me. If you haven't heard of it, Starlite was invented in the 1980s by a hairdresser named Maurice Ward. It was supposed to be able to resist blowtorches, laser beams, even nuclear level heat. He never revealed the full recipe, but ever since, people have tried to recreate it. Just search DIY Starlite on YouTube. There are tons of videos showing you how to make it with basic household ingredients. So I figured, how good is that version really? This is my version. It's made from 3 ingredients: cornstarch, baking soda, and PVA glue. It sounds simple, and it is, but with the right ratio, it turns into a tough, heat-resistant material that doesn't need toxic resins. Now, let's talk about the purpose of these ingredients. Cornstarch, which helps form a carbon layer when exposed to flame. Baking soda, which decomposes and releases gas that help with installation and foaming. PVA glue, acting as a binder to hold everything together. With these ingredients mixed into the right ratio, it carbonizes under heat but doesn't catch on fire or burn through. Let's talk about the first torch test at the beginning of the video. During this test, I used a basic infrared thermometer to check the surface temperature, but it maxed out almost instantly. It couldn't even register how hot the front side got. But the back side stayed surprisingly cool after a full minute of flame. It only read 75 degrees Fahrenheit, basically room temperature. I eventually cut open the disc to check the inside. The top layer had carbonized, but underneath it was still solid, no burn through, just clean material all the way down. That's when I upgraded to a higher powered infrared thermometer rated up to 1000 degrees Fahrenheit. Now I can actually see what the surface is doing in real time, and the results are even more impressive. This is Project 887. It held up way better than I expected. I'm not going to say too much yet, but there's a lot more I've been testing behind the scenes. This version of 887 is just one of them. More on that soon. Thanks for watching. See you in the next one.